Euclidean algorithm in the Gaussian integers. Okay? Will, everything's okay? Question or?
Yes, I'll probably.
Okay. Okay, so Euclidean algorithm in the Gaussian integers. The point was, again, it's the divisor. We had this, let's call it a lemma. We had this lemma in the integers. In fact, it seemed silly to prove it. That for every pair of integers n and m, of course now I mean Gaussian integers, there exist Gaussian integers q and r so that n is q times the quotient q times m plus r, and r is the remainder, and r is less than m, is what we would have written in the integers themselves, except this doesn't make sense in the Gaussian integers, so we use Will? Yeah, you could use the complex absolute value. There's something a little bit better to use. Well, it's equivalent. It's not better. The tradition, shall we say, is to use the norm. Where the norm, let me remind you, the norm where the norm of a complex number x plus iy is x squared plus y squared. So you're absolutely right. This is just the absolute value of x plus iy squared, the complex absolute value. Okay? Everybody see this? So let's try to prove this lemma. Now, in the integers, this was like, why are we doing this? This is everybody knows there's something called a quotient or remainder. That's what you did in grade school. Right? And by the way, in the integers, we also said the norm of r. We didn't say the norm of r. We said r itself will be non-negative. It's obvious that the norm is non-negative. We said r would be non-negative, means we chose a sign. Now we're not choosing a sign because what sign? You can multiply by I, you can rotate by 90 degrees and get a same size complex number. So it becomes a little bit more artificial which sign you choose. So we're not going to choose a sign. All we're saying is there exists a quotient and a remainder for any pair of integers. Of course, I need m to be not 0. Otherwise, the norm of n is 0, and you can't get a norm strictly less than 0. Okay? So this is the lemma. Let's prove it. What do we do? How did this work in practice? We did a few examples last time. Devendra? Perfect. Consider the complex number n divided by m. Now, okay, let's call this number, I don't know, z or something. The problem is, what does it mean to divide a complex number by another complex number? Other than Devendra? Sheik? Yeah, how? Remember we had like 4 plus 2i divided by 3 plus 7i.
Multiplied by conjugate.
Yes, exactly.
Conjugate of
What this means is multiplying by the conjugate and multiplying by the conjugate on the bottom, which gives us the complex norm squared, or equivalently this norm. This is the same thing as the norm of m. Okay? So here's the complex plane. Here are the Gaussian integers. Gaussian integers. And we get some number z in the complex plane. Does that make sense? So what should we make q? Other than Devendra. Will?
Is it the closest closest integer to that point.
Yeah, let's take q to be, typically we'll have 4 choices, and it doesn't matter which one we choose. All we want is to know that there exists something that we should call a quotient, not the quotient, but a quotient. So there exists nearby q in z adjoint I. Well, what does nearby mean? So if we choose this one to be q, what is how nearby? Say it again.
Near to n.
Near, this is z. This point is z.
Near to z.
Yeah, near z, exactly. Z is n over m. And again, I can divide by m because m isn't 0. So how near? Well, how close can I get to n over m? What can I guarantee? Not epsilon, other than Devendra. Drew?
Less than or equal to 1.
Yeah, I can definitely get less than or equal to 1. I can do even a little better than 1. So 1 from Q, a radius 1 circle is this big. So you're absolutely right. I can definitely get less than or equal to 1. I actually want to do a little bit better. Devendra. Yes. So look at this point. The worst case scenario is if this point, let me draw it somewhere else now. Here's your Z, and here's your Q. The worst case scenario is that it's right in the middle. And if it's right in the middle, then this is the farthest distance I would ever have to travel. And what is that distance? Well, what's this distance? Will?
1, 1. So it'd be a square root 2, and it'd be square root 2 over 2.
Yes, exactly, exactly. So this is a half, and that's a half, and by the Pythagorean theorem, that's root 2 over 2. So this distance is a half, and that distance is also a half, and that's the farthest I would ever have to go to reach a Gaussian integer, which means that this distance, the biggest it can get, is root 2 over 2. So this is, at most, root 2 over 2. Charles?
Are we picking the closest one?
So this is there exists, but does not mean that it's unique. A lot of times, most of the time, it will be unique if we want the closest one. But if you're dead center, or even if you're on one of the two center lines, one of the 1/2 lines, there's not the closest, there's a closest. And for the purposes of the algorithm, it doesn't matter. So because I put here root 2 over 2, that means I really want a closest, but even that isn't necessarily unique.
Right, we just can't pick the one on the other side, right? Because then it wouldn't be tested.
Right. If I'm near this point, I don't want to pick that point because that distance can be bigger than 1. And you'll see that this distance is exactly the thing that makes that a strictly less than sign. In fact, root 2 over 2, the thing about root 2 over 2, well, this is also 1 over root 2. And root 2 is bigger than 1, so 1 over root 2 is strictly less than 1. Or root 2 is 1.4 or something. So half of that is like 0.7. So that's strictly less than 1. If you chose the wrong point, so Charles's question, let's do another copy of this over here somewhere. If this is my Z, and I choose this point to be Q, and I'm bigger than the unit circle, I'm farther than this unit circle, then I chose the wrong point. I will not get a remainder that satisfies this inequality, as you'll see in a second. That inequality is measuring this geometry, what this distance is here. Okay, so if this distance to the nearest point is bigger than 1, I'm in trouble. So a closest point. So you're right, maybe there exists nearby, by which I really mean closest, but it's not the closest, it's a closest point. Okay? So, fine. What does that mean? So I can always find a q, so that q minus n over m in complex absolute value in that distance is less than or equal to root 2 over 2. So if I multiply both sides of this inequality by m, that implies, so let me multiply this by m, is less than or equal to, well, really I'm multiplying by the absolute value of n, which I can pull inside, 1 over root 2, absolute value of m. Does everybody see that? That's simply because I'm multiplying by m and expanding, and inside we have absolute values. Does that make sense, Sheik?
Just one question about like the distance between 2 points. Why is it half a distance between Q and the other point?
Because this distance is 1.
Okay.
This is from -2 to -1. So the lattice points, the horizontal lattice points are distance 1 apart, and the vertical lattice points are distance 1 apart. And so I shouldn't have to go farther than halfway horizontally to get a lattice point. I shouldn't go farther than halfway to get a lattice point vertically, which means the total distance is the diagonal. Does that make sense?
Yeah.
So what should I call this? This is now a Gaussian integer because it's multiplying and adding, subtracting. Gaussian integers form a ring. That was one of the exercises. So we can add, subtract, and multiply but not divide and stay within the Gaussian integers. When I divide, I leave the Gaussian integers momentarily. So this is what we should call
R.
R. Exactly, R. Or maybe negative R, the way I've,
It's gonna be R.
yeah. Maybe I want, and I mean, it's the same thing. So this thing on the inside, let's call it negative R because I wrote n minus qm is R. So this is mq minus n, so that's negative R. It doesn't matter. Okay? And look at what we see. R, the absolute value of R, which is, so if I square both sides of this, I get the absolute value of R squared, also known as the norm of R, is less than or equal to, I'm squaring this also, 1/2 absolute value of m squared, which is half of the norm of m. And the funny thing about a half is that it's strictly less than 1. So the remainder is strictly decreasing. Everybody see that? Question, Will, or? No. Does that make sense? Sarah, did I lose you? Not quite. Okay. There's a homework from today's Tuesday. There's a homework from last week that's due Friday that will force you to do a bunch of examples of this. Okay, you'll get a lot of good practice with this algorithm. Any questions? So once we have the division algorithm, now we can start looking at ideals generated by a bunch of Gaussian integers. Exactly the same thing that we did before. Let's go back for a second. Let's leave the realm of Gaussian integers. I didn't mean to go on to this tangent. You guys kind of egged me on. But I do want to finish the discussion in the rational integers, the usual integers, before getting to unique factorization in the Euclidean integers. Okay, so remember what we recall, before we got off track with this, we had proved that Z is a principal ideal domain. Everybody remember what that means? Any ideal, i.e., any ideal generated by numbers n1, n2, and so on, possibly countably many, there's only countably many numbers, is equal to a principal ideal. And in fact, you can tell what that ideal is. It's the GCD of all of these numbers. Okay? You remember this? We talked about this? Does this make sense? Now it's easy to prove some elementary properties of the integers. And those properties can be used for all kinds of good or evil, depending on what you're doing with them. Okay, so here's a proposition. So if an integer a divides the product b times c, and a and b are co-prime, then a divides c. Okay? If I take two numbers b and c and I multiply them together, and there's a third number a that's a factor of the product, and a and b are co-prime, then a has to divide c. Okay? Again, this is obvious in the integers, but false in some generalizations. So proof. Well, what does it mean for a and b to be co-prime? Let's look at the ideal generated by a and b. So look at ideal. So maybe I'll put GCD here so that it's clear that I mean the integer GCD. The ideal, which let me remind you is the set of all things of the form, ax plus by, where x and y are integers. So far, so good? Everybody knows exactly what we're talking about? What is this ideal? And d is 1. The GCD is 1, so we'll get all integers. In particular, the Euclidean algorithm, i.e., I mean, this is sort of circular because this is how we proved this statement. The Euclidean algorithm, in other words, the Euclidean algorithm gives a solution to ax plus by equals 1. Right? So there exists x and y. This was just on your quiz. There exists x and y so that ax plus by is 1. Great. So what? Dipendra?
Well, so it also gives a solution that x plus by equals c because 1 divides c.
It does also give a solution of ax plus by is equal to c, but how are we going to use this condition? We've used this condition to get that this ideal is all integers. Let's multiply both sides by c. Multiply by c, and what do you get? A times c times x plus b times c times y is equal to c. Everybody see that? So what? Is this a multiple of a? Does a divide this? So a divides this. How about this? Our assumption is that a divides the product of b and c. And here's bc. So a divides this. So this is a multiple of a, and this is a multiple of a. When you add two multiples of a, you get a multiple of a. This implies a divides c, which is exactly what we want. Okay? All right, but now we're very close to the fundamental theorem of arithmetic. These are the kind of baby steps that we need to get out to the fundamental theorem. So here's an immediate corollary. If P is prime, and P divides a product B times C, then P divides B or P divides C. This is the key property of of the primes. And again, it seems silly to do this in the integers because you've probably known this for 10 years or something by now. But you'll see this becomes non-trivial when we try to do it in other rings. So why is this true? Other than Dependra? Sorry? Well, I kind of gave it away. It's a corollary of this proposition. So it should be, corollary means it should be very easy to therefore conclude from what we just did the next step. So if you have something, if you have P implies Q or R, Drew?
It works because if P is prime, its only multiples are itself in one.
Perfect.
So you can't divide it between B and C, it can only fit in one.
Perfect. So assume P is prime, which we can, and P divides B times C, and P does not divide B.
Oh.
Then we have to conclude that P divides C. Kevin.
Doesn't that mean like either B or C is like B to begin with?
They don't have to be equal to P to begin with. B and C are not assumed to be primes. They're just arbitrary integers.
Okay.
So if I have, 18 times 30 has 5 as a factor,
Oh, okay.
then one of these has to have 5 as a factor. 18 doesn't. So if 18 does, then we're done. If P divides B, then we're done because we've concluded one or the other. So let's assume that P doesn't divide B. Well, if P doesn't divide B, what? Sorry?
It has to divide C.
Well, that's what we're trying to prove. We're trying to prove that it has to divide C, but Drew gave us a great hint, which is what's the GCD of P and B? The only divisors of P are 1 or P. That's what it means to be a prime. It only has 1 or P as its divisors. So the greatest common divisor is either P or 1. Our only options are P or 1 because P is a prime. Charles?
Oh, it can be P because then P would divide B, so it has to be 1.
Can't be P because P doesn't divide, P doesn't go into B, so the GCD isn't P. So the GCD is 1. Now we can use the corollary. A is now, A is now P, and A and B are co-prime,
So B divides C.
so B divides C. So P divides C. So use proposition with A equals P, that implies P divides C. Does everybody follow that? Follow the logic of that argument? So the only place where we use that P is prime is right here. There are only two options for the GCD, because the GCD is going to be a divisor of P. It's either 1 or P. If the GCD is P, then okay, P is already a divisor of B and we're done. If it's not, then the GCD is 1, and then we can apply the previous proposition. P divides B times C. P and B are co-prime, therefore P divides C. Cool? And what that means, so another corollary of this, let's do another corollary. So another corollary of this is that if P is a prime and A and B are integers, if P is a prime and A and B are arbitrary integers, then, I guess I haven't defined the ORD function, I will in a second. The order of P of A times B is the order in P of A plus the order in P of B. What do I mean by order? So predating this corollary is a definition. order of P of A. So this is order of P, maybe in A. So what's the, let's do some examples. Definition by example. What's the order of 3 in 18?
2.
18 is 2 times 3 squared. The prime factorization of 18 is 9 times 2. 9 is 3 squared. So there are 2 3's in 18. There are 2 3's in 18. So it's the largest exponent. It's the maximal k. It's the maximum k, so that p to the k is a divisor of a. When k is equal to 0, p to the 0 always divides a, so the order could be 0. If 3 to the 1 divides a, then you could try 1. 3 to the 2 does divide a, so we can try 2. 3 cubed no longer divides a. So that's it, we stop it. So this set is 0, 1, and 2. The largest of that set is 2. Okay? Nice, well-defined function. At some point, you try dividing your number by p squared, by p cubed. At some point, you run out, because eventually p to the k becomes bigger than a itself. So this has to stop. It's a finite list. What's the largest entry? It might be 0. The order could be 0. What's the order of 5 in 18? Altogether, 0. Okay? Does this make sense? So what this corollary is claiming is that the order function is additive. When you multiply two integers, the orders add. It's like a logarithm. I mean, it really is like a logarithm, right? Except it's not the usual logarithm. It's not, Napier's logarithm. It's the prime p logarithm function, the order function. Does that make sense? Okay. Great. So proof of the corollary. Question? If you're confused,
I was
please.
just wondering why, what the difference was actually between that and a log, but it's either an integer or a 0. Whereas
Yeah, well, log of 18 isn't 0. Log of 1 is 0.
Exactly. So
So-
with the log, it's either an integer. Sorry, with the order, it's either has to be an integer or a 0, whereas this is not true.
Right. Yeah. But this is the sense in which it behaves like a log.
Right.
I mean, it's a p-adic log. Whatever. We'll get to that. So let's prove this corollary. Okay, so let's ord sub p of a equal alpha. Oh, there's a notation for this. There's a good notation for this. So we'll write 3 squared, not just divides, but exactly divides 18. So this means 3 squared divides 18, but 3 cubed does not. It's another way of saying 2 is the ord base 3 of 18. Okay? So p to the k exactly divides a. In other words, p to the, this is going to look really bad. P to the ord sub p of a exactly divides a. So this double line means exactly divides. This is exactly divides, which means it divides, but no higher power of p divides a. Okay? So let ord p of a be alpha, i.e. p to the alpha exactly divides a, i.e. A is equal to p to the alpha times, let's call it a1, where the GCD of A1 and P is equal to 1. Does that make sense? So I'm just saying, what would that be in the case of 18? 18 is 3 squared. That's 3 squared times 2. And 2 and 3 are co-prime. Okay? So pull out as many powers of P as you can. You're left with something. That something is co-prime to P. Because if it wasn't, you would pull out another P. So far, so good? Okay. And similarly, let beta be the ORed base P of B. So B is equal to P to the beta times B1, and the GCD of B1 and P is 1. Does that make sense? So let's look at A times B. A times B is P to the alpha times A1, because that's what A is, times B. B is P to the beta times B1. So far, so good? Of course, that's P to the alpha plus beta times A1 times B1. And here's the part where we're going to use the fact that P is prime. Dipendra? So if P wasn't prime, if P was like 6 or something, it might be, you can do this with what's the order. I mean, it's a silly thing to do. Here's an aside. What's the order of 6 in 18? Charles? 1. 6 does divide 18, but 6 squared doesn't. Okay? How about what's the order of 6 in 12? Six divides 12, but 6 squared does not divide 12. So this is 1. Okay? What's the order of 6 in 18 times 12? 2, because it's a log, right? 3. Because 18 times 12 is, can anybody do 18 times 12? 180 and 36 is 216. And 216 is 6 cubed. That's why I chose 18 and 12. 18 is 2 times 3 squared. 12 is 2 squared times 3. And when you multiply them together, you get 2 cubed times 3 cubed. Okay? The order function is not additive in general unless you're dealing with a prime base. Okay, so that's the sense in which it doesn't really behave like a logarithm. It does on primes. That's what this corollary is trying to prove. For primes, it is additive. So to appreciate that, you should try it on non-primes and see that it's not additive. So 3 is not equal to 1 plus 1. Okay, so this is our enemy. And let's look back at this proof to see where our enemy arose. If P was not prime, it would be possible for this to get extra multiples of P. Even though neither of these are divisible by P.
Because let's say,
You just write that statement. If it was not prime, then
Yes. I'll write it in a second. Let me see what the bench
if
is.
it wasn't prime, then it would be like, say, GCD of B1 and B would not necessarily be 1.
Right. Right, what I should really say here is, and P does not divide B1. Because if it did divide B1, I would take it one step, I would replace beta by beta plus 1. And same thing here. Maybe the better thing to write pedagogically is P does not divide A1. Charles?
It would have to be B does not divide P, because if B divides P1, you would take that out already.
P dividing B1 means P is a multiple of B1. So how many 3's do I have inside B1? If I haven't taken out all the 3's that I can, then there's an extra 3 left over. Take it out.
Right, so are we talking about when P is not prime, or?
So we haven't used the fact that P is prime yet in the proof.
Okay.
We're about to now. Okay.
So what would the difference between P and B having GCD 1 and P dividing P1?
Let's do it right here. Here's the difference. 18 is equal to 6 to the 1 times something left over, which is 3. And 3, so what I'm saying is 6 does not divide 3.
But 3 divides 6, right?
In this case, yes. Yes, in both of these cases, the numbers I chose are such that B does divide P. But that, in general, so if I made this 6 times 5 or something, then it would be 6 times 6 to the 1 times 5, and neither direction is there a division.
But then in that case, the property should still hold because.
Yes.
Okay.
Yes. The thing that's going on here is that I didn't have an extra factor of 6, I didn't have an extra factor of 6, but when I put them together, I picked up the extra factor of 6. And I picked it up exactly here. And so what our proof is going to say is that you can't pick up another factor of P here. And that's where we're going to use that P is prime.
Because it's prime, okay.
Yep, exactly. Exactly. I want you to see this corollary. This is the key corollary that we're going to use. All right, well, we'll use it right here. But I wanted to, Sheikh, you asked me to write something down that was a good thing to write down.
If E was not prime, then it won't be additive. Order of the sum of orders of 18 and 11 will not be additive. Because C is not equal.
So that's exactly what this example shows. If P is not prime, then ORD sub P is not necessarily additive. We're trying to prove that when P is prime, ORD sub P must be additive. Okay? So if it's not additive, we certainly have at least alpha plus beta factors of P. So coming back to here, if the ORD sub P of A times B is bigger, strictly bigger than alpha plus beta, we know it's at least alpha plus beta because we already have alpha plus beta times an integer being A times B. If we picked up another factor, well, where did we pick it up? We picked it up here. Then P divides A1 times B1. Now 6 can divide a product without dividing either of the entries, but 5 can't. The previous corollary, by the previous corollary, that implies P divides A1 or P divides B1. And that's a contradiction. So this can't be true, which implies the order of P of A times B is at most A plus B, but it's also at least alpha plus beta rather. So the ORD sub P of A times B is equal to alpha plus beta, but alpha was the order of P of A, and beta was the order of P of B. let's go over that argument one more time. Okay? What are we trying to show? Let's slide things down. What are we trying to show? We want to know that this ORD function is additive. We already saw by example it's not necessarily the case for not prime values. What does it mean? What does it mean that the ORD set P of A is alpha? It means that you can get exactly alpha multiples in A, but no more. So if you pull out those alpha multiples, then P is not a divisor of what's left over. And the same thing with B. So if we look at A times B, I guess I do have to slide this up here. If we look at A times B, that's already P to the alpha plus beta, so the order is at least alpha plus beta, times A1 times B1. If we had a larger than alpha plus beta order, then P would have to divide the rest. We have exactly alpha plus beta out of here. If there are more powers of P, they have to come from here. But the corollary says if P divides A1 times B1 and P is prime, then it divides one or the other. But we assumed it did not divide A1, and we assumed it did not divide B1 right there. And so that's a contradiction. So there are no extra factors, and the order function is indeed additive. Cool? Questions? Comments? Corrections? Issues? Now we can prove the fundamental theorem. And then we'll be able to see, I guess I want this corollary. Okay, so theorem, fundamental theorem of arithmetic says that if n is an integer not equal to 0, then, how do I want to say this? Then n is equal to, well, minus 1 to us, it could be negative. So there's like, let's call this epsilon of n, which is 0 or 1. There exists epsilon of n equal to 0 or 1, which is just the sign, is n positive or negative, times a product over all primes, p raised to the ORD set P of n. So this is the prime decomposition, prime factorization of n. Most of these are 0. P to the 0 is 1. So for most primes, you're just multiplying by 1. But only for certain small primes will you get some contribution. Like 18. 18 is a product of 2 times 3 squared. So for the prime 5, the order is 0. So that's 5 to the 0. Just 1. 7 to the 0, 11 to the 0, 13 to the 0. We're multiplying by 1 infinitely many times. There are infinitely many primes. And then the only times we pick up an order are at 2 and 3. At 2 we pick up the first power, at 3 we pick up the second power, and then we're done, and that captures 18. So there exists sign, and this decomposition is unique. And this decomposition is unique. What do I mean by that? i.e., if I have some other decomposition, I mean the sign obviously has to be the same, but maybe I can write n as a product of powers to some other function. Let's call it e sub p. Suppose I had another representation of n as a product of primes to some powers. Maybe different powers. No, if they can't be different, then these exponents are just ORD itself. Again, I always feel very silly writing this out in such a formal and highfalutin way when this is something you've known for a long, long time because you've dealt with integers and you've factored integers. You will see the importance of statements like this only, or at least I don't appreciate it. Maybe you appreciate it already, which is great. I don't appreciate it until I see how it breaks. And we're going to see, we already saw a hint of how it breaks. We'll see more soon. So let's finish with the proof, which is very easy. Well, how do I want to say this? It basically boils down to the fact, so fix a prime, so assume n has a second factorization, n is equal to this sign p to the ep. Okay? Fix your favorite prime p. And apply ORD p to both sides. Okay? In other words, what we know is that ORD sub p of n is equal to ORD sub p of -1 to the epsilon n times the product over all primes, p. Let's call this, so we fixed the p. So let's run over the primes, let's call them q. So as not to confuse with the fixed prime p. Let's see, I'm going to lose some of you right now. I'm just changing, this p is a dummy variable. It's like when you're integrating dx and then you realize you want x to be a function, so you change the dummy variable to dy or dt or something. So I'm just changing, this is a dummy variable. I'm going to sum over, I'm going to take the product over all primes p, p to the ep. That's the same thing as taking the product over all primes q, q to the eq. Q is just a dummy variable for the set of all primes. Here, p was a dummy variable for the set of all primes. Okay? Did I lose anybody there? So now I'm going to fix one p, so I don't want to call this product over p's. I'll call this product over q's. I'm changing my dummy variable, sorry. Okay? What did we just prove about the ORD p function when p is prime? It's additive. It's additive. That means, this is by our corollary, that the ORD p function is additive. I can take any integer, so then I get a sum over all primes q of ORD p of q to the eq. Let's see, maybe this note.
Sorry.
It's okay. It's pretty cool. Thanks. Maybe this notation is what's confusing you. Is everybody comfortable with this notation? You know what this means? This product notation?
Yeah.
Does anybody not know what it means? Be honest. Yeah? Okay. What this means 2 to the e2 times 3 to the e3 times 5 to the e5 times 7 to the e7 and so on. Now, again, it might look weird to take an infinite product over all primes to all these exponents, but almost all these exponents are 0. And so then you're just multiplying 1 infinitely many times. Multiplying by 1 doesn't do anything. It's only the first couple of primes that actually contribute to this. Okay? So because this is a product, ORD behaves like logs. It turns products into sums. So this is a sum, ORD sub p of 2. So this is, let's write this out. This is ORD sub p of 2 to the e sub 2 plus ORD sub p of 3 to the e sub 3 plus, and so on. Okay, does that make sense? All right, so all we have to do is evaluate these individually. So, what is ORD sub p of -1? Well, either plus or minus 1. Those are your only two options here. How many times does the prime p go into 1 or -1? All together? Oh, okay. Now I've confused you. Now I know I lost you. This is it the epsilon n that's confusing? This is either 0 or 1. I just want to know the sign. But it's an integer. It's an integer, so our corollary about the ORD function being multiplicative applies to it just like it applies to anything else. So this is an integer. These are all integers. So I can break everything up by the Word function. Alex, I lost you. Back me up.
Yeah.
I'm sure I lost a lot of people in there.
Following, but like halfway.
Halfway. Keep going and we'll review. I'm almost out of time. Well, I am out of time, but we're going to go 1 minute over.
I need to decide to see the actual numbers.
Okay. All right. We'll do it again with actual numbers, but let's just very quickly finish the calculation. This order I claim is 0. P does not divide either 1 or -1. For primes not equal to Q, for Q not equal to P, wards of P of Q to the EQ. How many times does P go into some products for somebody else is 0? And all right, I'm just rushing now, and we will do this again. We'll do this again on Friday.